Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Denya Akhtar Berazali. My matrix number is 2213723853, and I'm going to present my mini project PBL. So I'm going to start with introduction. Okay, as you can see, here is the design, the closed loop digital control system, which is to control the cube servo motor with an inertia disc attached, which can point to any specific angle direction. Okay, for the first setup, we set the current motor voltage to 1, and then the input is set to 0 degree.
I'm Muhammad Haris Akmal bin Muhammad Babu Hisham, matrix number 2213722350, and I will do the block diagram explanation. So this is the block diagram of our closed loop control system for the cube servo created in LabVIEW and running on my rail. It uses feedback from the encoder to rotate the motor based on the user's angle. So the first one is user input. Set point is in degrees. At the top left corner, the block label input also allows the user to enter a desired angles in degrees. This is the target position for the motor. And the next one is conversion to radians. The user inputs is passed into a grain block, and then which converts the degrees to radians because the control system and encoder work with radian units. And the next one is encoder feedback, or CLHIL. At the bottom left, the encoder feedback block reads data from the encoder attached on the cube servo. The encoder gives us the actual position of the motor shaft in terms of counts. And the next one, we have counts to radians conversion. The encoder counts are divided by 65536 and then multiplied by 0.00307 to convert them into radians. These give us the actual angle of the motor disc in real world units. And the next one, we have error calculation. Both the user input in radians and the actual position also in radians go into the summation block where subtraction is done, and the formula follows by error equals to desired angle minus actual angle. So basically this error tells the system how far off the motor is from the target position. The next one, we have motor control signal. The error is then passed into another gain block labeled motor voltage. This block scales the error into a voltage signal suitable for controlling the motor speed and direction. Next one, we have signal output to motor, CLHIL, right? This control signal is then sent to the cube servo motor using CLHIL right block, which outputs the correct voltage to move the disc. And the next one is monitoring and visualization. On the right side, the system sends both the desired position and the actual encoder signal to a graph labeled XY graph. This graph shows the real-time response of the motor, so we can compare how well it follows the input angle. There's also a collector block and position and step signal motor for recording displaying system behavior. The last one, we have loop control. This entire system runs inside a control and simulation loop, which allows the program to continuously check the encoder feedback, calculate the error, and update motor signal in real time. A stop button is also included to manually halt the simulation whenever needed. So overall, this block diagram represents a full closed loop control system and rates the user's target angle, calculates the difference using encoder feedback, adjusts the motor voltage, and continuously updates the motion until the cube servo disc reach the correct position. That's all from me.
My name is Khairul Zahin. For my part, I'll be discussing the initial phase of our experiment, where we guided the inertia disc from its starting angle of 0 degrees to a target of 180 degrees. This tells the cube servo system to rotate the inertia disc to the 180 degree position, which means moving in the clockwise direction from its current angle. The closed-loop control system uses feedback from the encoder to detect the current position and compare it to the new target. Because the new target is the positive direction, the controller applies forward voltage to the motor. This causes the disc to rotate clockwise, increasing the angle value over time. In the graph, this movement is shown as a smooth upward slope, which means the output angle is increasing as the disc moves towards positive 180 degree. Once the disc reaches the 180 degree point, the graph becomes stable again, showing that the system has accurately reached the new position.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akram, and I'm gonna explain to the output graph when the input is negative 180 degrees. When the input is set to the negative 180 degrees, it tells the tube servo system to rotate the inertial disc to the negative 180 position, which means moving in the counterclockwise direction from the current angle. At the time, the disc was already at plus 180, so the system needs to rotate back to 0 and continue until it reaches negative 180 degrees. The closed loop system uses feedback from the encoder to direct the current position and compare it to the new target. Because the new target is in the negative direction, the controller apply reverse voltage to the motor. This causes the disc to rotate counterclockwise, reduce the angle value over time. In the graph, this movement is shown as a smooth downward slope, which means the output angle is decreasing as the disc moves toward negative 180 degrees. During this movement, we can also observe a small percent overshoot or PO in the graph. This means the point slightly went past negative 180 degrees before stabilizing back to the exact target. Once the disc reaches the negative 180 point, the graph becomes stable again, showing that the system has accurately reached the new position. Thank you.
Okay, so now I will compare the system response for 180 degrees and negative 180 degrees. As you can see, when we set the angle to 180, the disc will rotate clockwise, and the graph shows a smooth upward line as the angle increases. For the negative 180, the disc will rotate counterclockwise, and the graph shows a downward line, meaning that the angle is decreasing. In both cases, the system uses feedback from the encoder to keep track of the disc position and adjust the motor until it reaches the target angle. We can also see a small overshoot in both graphs. As you can see, the pointer will go slightly past the target, then it will correct itself and settles. Overall, both movements are smooth, stable, and accurate, showing that the control system works well in both directions. So thank you for listening to our presentation. So I will end it with a conclusion is that our group successfully designed and implemented a closed-loop digital control system using LabVIEW to control the inertial disc of a cube servo motor. The system met the design objective and responded accurately to user-defined input angles. Thank you.